In this video, I'm going to complete the most technically demanding part of the derivation of a path integral representation for the propagator that was introduced in the previous segment. And here again I show the expression for this propagator that we derived. So in the following, I'm going to be doing my calculations mostly in one dimension for the sake of simplicity. There is no real reason to go to one dimension, so the calculation sort of goes the same way in 2 dimensions or 3 dimensions or 100 dimensions. It's just going to one dimension, it just simplifies notations a little bit. We don't have to deal with vector indices. And also it will allow me to illustrate certain steps of our derivation in a sort of intuitive pictorial way. So the second comment I would like to make is that what we call the propagator also appears in the literature under the name of transition amplitude, well, from an initial point xi to a final point xf in this case. And a very closely related object is also called the green function. So if you see these expressions in the literature, they may be actually very much related to one another and all refer to this object essentially. Now, the main difficulty in calculating this object, once again, is the presence of this evolution operator, which is an exponential of Hamiltonian. And to calculate this exponential of an operator is a very tricky business. So basically the goal of the remaining calculation, as we discussed, is going to be to simplify this expression so that it doesn't really contain any operators. And we deal with sort of regular mathematical quantities, not operators. And in doing this simplification, we're going to rely on two very useful mathematical, or physical actually in this case, two formulas. So one of them, the first one listed here, we already have actually discussed in the second lecture last week. So this is the so-called resolution of the identity operator. And the fact that it is the identity operator means that so let's say if we have an arbitrary wave function psi, and we act by this operator on this wave function psi, so what we're going to get is the following: x psi, this matrix elements, times the ket vector x dx, and this is identically equal to the psi itself. So this is formula number one. Another equation which is going to be very useful, actually it's a property of the evolution operator, actually relies on a very simple observation. So the evolution operator itself translates the wave function from the initial moment of time, so this is time and this is, let's say, time equals 0, so to the wave function psi of t at the final moment of time t equals t. Well, so, but instead of going directly from 0 to t, we can do that in sort of 2 steps. We first can go to, let's say, certain t1, which is between 0 and t, and then go from t1 to t. So, going from t1 to t corresponds here in the language of this evolution operator is applying this operator with which depends on t minus t1 to the wave function that we have here in the middle. So on the other hand, the wave function in the middle, this psi of t1 itself, can be represented as the action of the evolution operator u of t1 on the original wave function psi of 0. So therefore, what we derive here is that the evolution operator u of t can be written as the product of two evolution operators u of t minus t1 times u of t1. Now, so the particularly simple way of splitting the time interval into two, in this case, is just dividing it in half. So let's say again, so we have this time axis, so 0 t, and we just divide it into 2 pieces. So from 0 to t2 and from t2 to t. And so therefore we have the expression for the evolution operator u of t is equal to u of t over 2 times u of t over 2. So now, if we're going to use the if we're going to focus on the actual propagator, which is the matrix element of this evolution operator between the initial point xi and the final point xf, what we can do, we can write it as xf u of t over 2, u of t over 2, xi, and insert here the resolution of the identity that we discussed in the previous slide. So, and if we do so, we get to this expression, which essentially splits the original propagator into two propagators. One goes from xi to x, and the other goes from point x to the final point x sub f. This splitting of the original propagator into two allows a very useful and intuitive illustration that I'm going to present now, which will actually bring us closer to the notion of path integral. So let's say this is my coordinate x, and this is time t. So, and this is my 0 and final time t. This is going to be my xi and xf. And so what I'm interested in is calculating the propagator of going from the initial moment of time xi to this xf at t equals t. So this is essentially what I'm calculating. And this sort of solid line connecting the 2 points sort of corresponds to my g of xi, xf, t. Now, this equation tells me that I can take, well, a point in the middle, so this is going to be my t over 2. And what I have to do in order to calculate this propagator, I have to consider all possible coordinates in between. So let's say I will go from xi to x, and from x to xf. This is going to be one path. Another path is going to be to go to a different x, like as so, etc., etc. So these solid lines are going to be sort of representing, the first and the second propagator in this integral. And well, obviously, this procedure of splitting the original time interval and position interval into two can be continued. So what I can do, I can keep on truncating my my time interval into smaller and smaller pieces, and when I continue doing so, I will have more and more intermediate coordinates that are going to appear, and therefore I will generate all possible trajectories that are going to cover the entire space here. And this is how path integral, or integral over trajectories, really appears. But at the level of this illustration, this path integral, this picture, is not very useful for sort of practical purposes. To make some progress here, so let me sort of formalize what I just said. And what I said is simply the fact that let me just split, instead of splitting my time interval into two pieces, let me split it into n pieces. And so n here is going to be very, very large, so that t over n, each individual time interval, is extremely small. And so each of these small time intervals, the evolution operator on each of these small time intervals corresponds to this exponential e to the power I over h bar h t over n. So this t over n I can make as small as I want. So, and if I make it really, really small, so instead of writing the full Taylor series for this exponential, I can write it as simply two terms, one minus the first linear term. And just I truncate my series right here, and so basically approximate my evolution operator in each of these time intervals as so. So as a matter of fact, you can say that I shouldn't have done this derivation. So because in the end of the day, what I have actually derived is that e to the power minus I over h bar h Hamiltonian times t is equal to 1 minus I over h bar h t over n to the power n, where n goes to infinity. And this is actually an alternative definition of the exponential. And this is absolutely correct. This is all there is. So we are basically just writing, instead of writing the complicated nonlinear function, well, exponential of an operator as a complicated function, we are just going to write it as a product of functions which are linear in our Hamiltonian. And as we do so, in between each of these terms in this product, I'm going to insert my favorite resolution of the identity. So this dx, x, x. And, well, since I have many x's now, so I'll have to label them differently. So there's going to be x1, x2, x3, which will sort of correspond to these intermediate coordinates that I have in my trajectories. Now, if we put everything together, we get this complicated looking expression for the propagator, which is obtained by, well, sort of sandwiching this product of evolution operators between xi and xf, and here I'm also going to be using the notation x0 is the initial one and x sub n is going to be the final one. So this will allow me to write this propagator in a more compact way. And also, as I mentioned, so in between of each of these sort of small evolution operators for a small time, t over n or delta t, so I insert this resolution of the identity, but I have to distinguish different instances where I have to do so, and therefore have so many different integrals. Now, the reason again I'm doing this is because instead of dealing with this complicated exponential, I now can deal with this linear matrix elements of the Hamiltonian, which can be calculated in a rather straightforward way. So just to summarize, what remains to be calculated, if you just look at this expression, is, well, simply the matrix element between x sub k plus 1 and x sub k, and the matrix element of the Hamiltonian. So all these guys, I, h bar, n, and t are numbers, so they don't really act on these functions. And the Hamiltonian itself, of course, is just basically the operator corresponding to the energy, and it has the kinetic energy part and the potential energy part. And so, apart from this matrix element, I have to calculate two other matrix elements, which essentially are the last pieces of the puzzle that requires to be completed in order to get this Feynman path integral. And so in the remaining of this video, I'm going to be calculating basically these guys.